Today we're going to talk about addition and subtraction of rational numbers. I sort of mentioned this in passing last time. I mentioned it when we talked about denseness and about how adding and subtracting fractions is really not always the easiest thing to do. And it's really great in that particular instance because we had another way to find a number between two numbers that we could utilize that avoided the whole adding the fractions part. But now we're actually going to talk about what that actually looks like to add fractions together. In particular, if fractions have common denominators or like denominators, it's relatively simple. You add across the top, you keep the denominator the same, and you simplify if there's anything to simplify when you're done. When the denominators are not the same, it's not quite as straightforward. So one way or another, you need to get the denominators to actually be the same. The book presents this way, and one of the benefits of this particular way that they present it is it does work all the time. And that's kind of nice to be able to say, this is your go-to fallback. If nothing else works, you can always do it like this. So if you'll notice what they've done is they've, and I'm going to draw sort of a visual for it, is that they've multiplied the denominators together, right? So there's the new denominator. And then they've done the diagonals. So we've got diagonal right here, so it's AD. And then you've got the other diagonal, for some reason my stylus is not working today, and then your other diagonal right here, which is BC. Visually, it's very appealing, right? I multiply one diagonal, I add the other multiple of the other diagonal, and then I multiply the bottoms together. It's very nice. It's not always the most helpful way of doing things. Sometimes it's easier than that. This can produce things that are not in simplest form. I mean, all methods can, but this one has more potential for that. So you may have more reducing to do when you're done if you do it this way, but it will always work. So we're going to do a couple of examples. On the first one, we're adding 1/3 and 5/3, and the denominators are what? 3. They're the same, right? They match. So when the denominators match, we simply add across the top. So we've got 1 plus 5. We keep the denominator the same. It's 3. So 1 plus 5 is 6. And when we get to this point, 6 over 3, if it can reduce, we're always going to do that. If it can't, then we're done. This one, of course, does reduce. And what is 6 divided by 3? 2. Visually speaking, 1/3, I'll draw 1/3 in this box. And then since 5/3 is actually, more thirds than 3, I need 2 boxes. So when I'm talking about, and this is just a ballpark idea of what's going on, of course, whoops. You can see why it's one of the things that students really struggle with sometimes is they want to add across the top. They're good with that, but then they want to add across the bottom. And we want to make sure that we understand why that doesn't really work. So here's 1/3, right? And then 5/3 would be 1, 2, 3, 4, 5. And you can count that we actually have 6 shaded in pieces. And the denominator has to do with how big they are. Well, they're of size 1/3, right? They're each a third of a box. So that's why there's 6 thirds. There are 6 individual pieces of size 1/3. So this would be one visual of why that's happening. The other thing you could do is that you could always start out with, if you wished, the bigger number. So here's my 5/3 picture, right? No problem with drawing that 5/3. And then say, well, I need to draw in one more third. Where would that one more third be? Well, look, there it is. What's my answer? Well, it's 2. I've got 2 boxes fully and completely shaded in. It's another way to justify why that's working for us. All right, so like denominators are very friendly. Unlike denominators, not so friendly. Now, on this one, what we're about to do, the method that your book shows, works very well because the denominators are quite small and they don't have anything in common. 4, 3, great. I don't have any, like, it's not 4 and 2, or it's not 3 and 6, or 3 and 9, or something like that. So they don't have anything in common anyway, so it is very friendly to try to do it the way that your book is showing you will always work. So the first one, that's kind of a light color, let's do it a little darker. This first diagonal right here, I would have 1 times 3. So I'm going to actually write it out just so that you remember where each of the pieces are coming from. You don't have to. But the first diagonal would be 1 times 3, plus the second diagonal, which is 5 times 4. And then it divides by the denominators that are being multiplied. So in this case, 4 times 3. So that's actually what the method described on that first slide. And then we'll do some multiplication and simplify what we have. So I have 3 plus 20 over 12. 3 plus 20 would be, of course, 23 over 12. I'm going to tell you the same thing I tell my actual 5th graders that live in my house all the time. If nobody tells you that there's something wrong with improper fractions, there's nothing wrong with them. Okay? If a book tells you, or if a problem tells you, or a test tells you, or whatever you're working on to make sure that you have your answers in a certain form, then it matters, and you need to change it to whatever form it suggests or requests. But if it doesn't ask you to, then this is a perfectly reasonable place to stop. And most of the time your book does that. It just lets you stop with where you are. So yes, it's top heavy. Yes, it's an improper fraction. And no, I don't care. I just don't care. It doesn't matter. This is a perfectly reasonable answer. Now, if the 23 and 12 had something in common, right, like they both had a 2 in them, or both had a 4 in them, or a 3 in them, we would want to reduce it. We're not going to leave it there. But changing it into a mixed number is not any better of an answer than an improper fraction. So this is good. Any questions on that one? All right. Now that I've told you that there's nothing any better about them, we are actually going to talk about them, namely mixed numbers. Mixed numbers are used in everyday life to represent values that are an integer combined with a proper fraction. So an integer means there's a whole part at the beginning, like a 5, like a non-fractional part. And then a proper fraction means you've got a fraction afterwards where the numerator is in fact smaller than the denominator. So, for example, I said it occurs in everyday life. I ate 2.5 cookies. Whoa, not cookies. Cookies. Mixed numbers are very hands-on. You say 2.5, and you guys all had a picture of what I meant, especially once I attached the word cookies to it. You pictured 2.5 cookies. I didn't have to even draw it, right? You knew what that looked like. The reality is that 2.5 is actually equal to the fraction 5 over 2, but if I came in and I told you I ate 5 halves of a cookie, you would all say, and then you'd have to figure it out, and then you'd have a picture in your mind, right? It's not instantaneous. We don't think in terms of not or improper fractions in our brains when we're working on it. It's just not a concrete image we get, okay? So yes, it's equal to 5 halves, but to be honest, 2.5 is a far more common way of writing that in everyday problem solving. That said, mathematically, it's often easier to work with something that's either a fraction or a whole number and not something combined. Working with a mixed number is often not very friendly. So you see people change in and out of these forms for that reason, really, okay? So we're going to talk about how we change in and out of these forms. For example, 14 over 3. All right, so 14 over 3, what does that bar in the middle actually mean? Divides. It means division, right? So this is exactly the same as saying 14 divided by 3. Agreed? So if we're trying to change something to a mixed number, we're actually doing a division problem. That's it. So we're going to do 14, and we're going to divide by 3. If you have to write it out, do. If you can do it without that, that's great. I don't care. But how many times is 3 going to 14? 4 times. What's 4 times 3? 12. And if I subtract, I get a 2. Around 5th grade is when students are working at moving numbers in and out of mixed numbers. Okay, into mixed numbers, out of that. Okay, so we're looking at an answer here Before that, in 4th grade, what my kiddos are doing right now because they're still doing reviews, they write this as their answer. Do you remember seeing that as an answer, 4R2, right? And it's a perfectly great place to start, but that's not where we are right now. We're working at finding out the mixed number when we're done. So our answer is actually going to be expressed as 4, and then what I have is this 2 at the bottom still as a leftover part of 3. So this would be 4 2/3. Any questions on that? By the way, we're all going to have to be under the mindset of that all of the things that I teach you mathematically are things you've been taught before. I know that. That doesn't mean you always will remember them. And I know that too. So if that happens, please feel free to ask me a question. I'd much rather you know what I'm doing than be like, I remember we did that before, but I still didn't understand at the time she said it in class too. So if you don't want to do it in class, come see me after class so that we can chat, okay? All right, so we've taken an improper fraction and we moved it into a mixed number, and we're going to go the other direction now. We're going to take a mixed number and turning it into an improper fraction. First rule of thumb, if it's a negative, I would ignore the negative until you're all the way done with the problem and just put the negative on. Operationally, it's not useful to have it in the middle of your problem. We did that last time where we were looking at cross-multiplying. I said, we know that they're both negative. We don't have to focus on that. So when we're taking a look at, in this case, 3 5/8, I want to show you first sort of like the shortcut of what we do all the time, but then I'd kind of like to show you why it works too, because it looks a little bit like that hocus pocus magic-y stuff, and that's not what math is. Math should make sense. So what we do, like the process, is we say 8 times 3, and what do we get? 24. And then we add 5 to it, and we get 29. And our answer is 29 over the 8. And it's negative because it started out as a negative 3 5/8. That's what we do. It's shortcut, works really nice and easy, like multiply, add, multiply, add. You can do those multiplication additions, but I'd like to show you why it works. Why in the world am I multiplying 8 times 3 and then adding 5 to actually find this answer? Well, even when you say it, you use the word and between these, right? And is another phrase that we sometimes will use interchangeably with addition. This means 3 plus 5/8. Everybody get that, okay, right? 3 5/8 is 3 wholes and 5/8 plus 5/8 more. Well, the only way to add fractions together that don't have like denominators is to get them to have like denominators. So this is really like 3 over 1. I need a common denominator. Well, how do I get that? Well, let me show you another way of doing that I didn't show you before. I mean, we can do the fancy, crosses in the multiplication on bottom like I did a minute ago. But another way that you're probably familiar with is by multiplying the top and the bottom of a fraction by the same value. And lo and behold, do you see the 24 now? It's 24 over 8 plus 5 over 8. That's where the 24 is coming from. It's because we're actually changing the 3 wholes into 24/8. And then the reason I add the 5 to it is because I'm actually adding 2 fractions together after that. 24 plus 5 is 29, of course, at that point. And yes, it's supposed to be negative. One of the properties of all integers that we saw back in chapter 5, for those of you who've been with me through number theory, is this idea of an inverse. And it works for all rational numbers as well. We're talking specifically here about an additive inverse. For any rational number a over b, there exists a unique rational number negative a over b, such that when you add them together, you get 0. So we saw 5/3 a moment ago. What would I have to add to 5/3 to get back to 0? Negative 5/3, right? That's its additive inverse. So this is a property we saw in chapter 5, and this is another property we saw in chapter 5 that extends to rational numbers. If A over B and C over D are rational numbers that are equal, right? So imagine you have 3/6 and 2/4. They're the same, they just are expressed differently, right? Then for any number E over F, if you add it to A over B and you add it to C over D, you're going to get the same outcome. Okay, so I always use this type of an example, but it works really well, and I wish my daughter were in class with me today. My 14-year-old daughter is almost identically, and for the purposes of this argument, we will say identically the same height as I am. Okay, we're the same height if we're both standing up here in front, right? So if I put on the 2-inch heels and she put on 2-inch heels, we would be the same height. And that's all we're doing here. We're saying if we take two equal quantities and we add something to them that's the same, they're going to stay equal. And of course, we've used this all over the place in your algebra courses, right? When you're solving equations, right? We shift things around, we move them so that we can solve and isolate x by itself, that kind of thing. That's actually a property of equality. I want to show you, using that property of equality, two different ways to work with mixed numbers. So we're going to solve this equation. To solve this equation, that is to get x by itself, what I need to do is I need to add the 2 1/2 to both sides. And once I do, I'm just going to write it out sort of horizontally now. I end up with 3 1/3 plus 2 1/2, right? And I'll have the answer once I can sort of combine those together some way. Okay? There are two methods for doing this. And it doesn't matter to me which one you use, unless, again, somebody asks you to use one specifically. I have been known in the past on tests to say, do it two ways. So I want to see that you do know both of them sometimes. But I want to show you two ways of doing it. And part of the reason I want to is that I always think it's good to have more than one way to do something. So when you encounter the child that doesn't like the way you just showed them, you have something else to show them. Even if you don't remember it on the spot, you have the ability to say, I've seen something else before. Let me come back to that tomorrow. So the first way that I'm going to do it is the way that I learned. This is the only way I learned as a student, and it worked fine for me. So, it will probably work okay for some of your students, and it's probably what some of you have seen. So this way, number one, my first method, is going to be the improper fraction way. There's pros and cons to both ways, by the way. So the improper fraction way says that I'm going to take each of my mixed numbers and I'm going to change them into improper fractions, which we just talked a minute ago about how we would do that. So shortcutting it, right? 3 times 3 would be 9, plus 1 would be 10. So my first improper fraction is 10 over 3. On the second one, I've already seen this problem today, and you have as well, right? 2 times 2 would be 4, plus 1 would be 5, so I have 5 over 2. So one way with improper fractions is to change them both into improper fractions, and then do whatever you need to combine them together. So just for us to practice again this method that your book shows, I'm going to do it this way. So 10 times 2 would be 20, plus 3 times 5, which would be 15, over, and then I multiply the bottom together, which gives me 6. And then I need to simplify. So 20 and 15 would be 35. So I have 35 over 6. Now, I said something earlier about the fact that if it doesn't tell you it's a bad way to write the answer, you're good to leave it that way. Well, here's a caveat to that. If the question starts out with mixed numbers, the answer should be in mixed numbers. Makes sense, right? If somebody comes in and starts talking to you about fractions and you start giving me answers in decimals, we're not talking about the same expressions of those numbers. So we're going to stick with whatever we start with. So I need to turn that back into a mixed number to get my actual answer. And we did that before as well, right? So it's division. 35 divided by 6. How many times will 6 go into 35? Almost 6. 5. 5 times 6 is 30, and I subtract to get 5. So this answer ends up giving me the 5 that's on top, and then the 5 over 6 that's the remainder at the bottom. So this is where my answer is. All right, so on this problem, it works pretty well. This method is not a bad method to use with these particular numbers. However, if you didn't have 2.5 and you instead had 22.5, hopefully you can see how quickly you could get large numbers, right? Because then you're going to take that 22.5 and you're going to change it into a mixed number that's then going to get that value multiplied by the denominator. I mean, it's going to get big. And you're going to be working with things that get very large. And that's kind of a drawback. You know, the bigger the numbers get, the harder they are to work with. So that's kind of the thing on that one. Improper fractions. The second way to do this problem is to do it with mixed numbers. In other words, we're not going to put it in improper fractions at all. So how does that work? Well, what we do is we reorganize things. We put the whole number parts together and we put the fractional parts together. So instead of having 2.5 plus 3.5, or sorry, 3 1/3, we would have 2, or I'll do it in the order they've got it here, 3 plus my 2, and I'll shift my 1/3 to be next to my 1/2. And I'm allowed to do that because addition is commutative. Commutative means that we can switch the order of things and it works just fine. So the nice thing about that is that I have 3 plus 2, there's 5. And while, yes, I do have fractions at the end, the fractions are lots smaller numerators than they were in the other method. So that part's kind of nice. And I can do the same thing I just did before. I can do 1 times 2, which is 2, plus 1 times 3, which is 3, over 3 times 2, which is 6. So if I add my numerator together, there's my 5 and 5/6. Now again, on this problem, it worked out really nicely. This method works really well. But what happens if I add those two numerators together and it ends up being an improper fraction? Well, then I got some more work to do. I can't leave it as a mixed number is not a whole number and an improper fraction. It has to be a whole number and a proper fraction. And we'll see an example of that happening in a moment, so you can see what would happen if I ended up with it being top-heavy on that part. All right, let's take a look at subtraction. Subtraction of rational numbers. First, a definition. If a over b and c over d are rational numbers, then a over b minus c over d is the unique value e over f, such that a over b equals c over d plus e over f. And I'm trying to present it the way your book does. Sometimes I feel like all those letters just made it way harder than what it really was. So let me just show you the way it works with some whole numbers really easily so that you can see what happens, because it works the same way with subtraction for rational numbers. So the reason that 5 minus 2 is 3, the reason that's true is because 5 is the same as 2 plus 3. And that is all that definition is saying. The only reason e over f is the actual value of the answer is because if you add e over f to c over d, you get back to a over b. Right? In education, you guys have probably heard the phrase fact families. Have you heard that before? This is what's meant by this. These two would be in the same fact family. In theory, if a child knows that 2 plus 3 is 5, they should be able to get to the point of understanding that 5 minus 2 is 3 and 5 minus 3 is 2. They all go together, all right? The last one here on this, or the second one on this slide, Theorem 6.8, says that subtraction is really the same as adding a negative. We talk about that also in Chapter 5. A lot of these are hangovers from Chapter 5. So that when we have positive versus negatives, or if you think of values being subtracted versus added, there's a connection between them. The next slide looks exactly like the addition slide, but with subtraction in between. If you have the same denominators subtract, you just subtract across the top. If you have different denominators, you can do this sort of, somebody called it one time a butterfly for me. You see my butterfly? You can do a butterfly. right? And then you can multiply along the bottom. Okay, so a reminder to those who, it looks like I've got a lot of people writing on paper today. All these notes are printed inside of Canvas, so if you haven't had a chance to get there and do that, probably be a good help to do that so you don't have to write quite as much. All right, so let's do an application problem for why and where and how as an example of one. Subtracting fractions or adding fractions actually comes into play. So Martine bought 8 3/4 yards of fabric. She wants to make a skirt using 1 7/8 yards, pants using 2 3/8 yards, and a vest using 1 2/3 yards. How much fabric will be left over? So to start with on this problem, do we need to add or subtract, or do we need to do both? What do you see as you read it? Because there's more than one way to do this problem, even just in reading it and understanding it. What would you write down as your first step of what am I trying to solve? And then do what? You definitely could do that. So you could add up all the things that she's trying to make. So on hers, she has 1 7/8. Whoops, let me get the black. She has 2 3/8. And then she has 1 2/3. And you could then, after you've added them together, like you said, subtract them from the amount of fabric she has, which is 8 3/4. Did anybody think of it differently? Good. Yeah, and in reality, that's kind of what you physically do when you create this, right? She's probably got patterns that she's going with, so she knows how much she needs for each of these. And she would actually take the 8 3/4, and then she would cut off the piece that she needs for the first item she's making, right? So it would be subtracting it off. And then she'd physically cut off the next piece and go off the third piece. So that would be another way to think about it. So instead of thinking about adding several things together, we would just think about repeatedly subtracting things. And it doesn't matter which one you do. What you should recognize, however, is this is the example that I was referencing earlier about mixed numbers, okay? And I'd like to do it with the improper fraction approach first, I suppose. And we will just see how that works out with improper fractions. So let's take a look at each of our fractions. Let's just do the part that's in parentheses first, okay? So if I have 1 7/8, how can I change that to an improper fraction? What would it be? 15 over 8, you bet. What would 2 3/8 be? 19 over 8. And then 1 2/3? 5 over 3. It probably is sort of wise to recognize that the first two have the same denominator, and we might as well add them together before we go getting all creative with everything else, right? So I still have at the beginning my 8 3/4. We'll come back to him in a minute. I don't even need to mess with him right now. 15 and 19, what is that? 34? Okay. 34 over 8 plus 5/3. So how am I going to add those together? Yeah, we need a common denominator, and especially since 8 and 3 don't have anything in common, it would be just as nice to sort of do the method that they're showing visually that we've been working with. So what is 34 times 3? It's supposed to get real big real quick. What is it? 102. 8 times 5. That one's 40. And then 8 times 3 on bottom is 24. Now, I'm wanting to take that away from 8 3/4, so it's probably a good point now to go ahead and change that into an improper fraction, either this step or the next one. If I change that into an improper fraction, what is 8 3/4? What is it?
35.
Yes. Okay, so now I have 35 over 4 minus 142 over 24. Okay, so you could, and you can if you wish, multiply across here, and multiply across here. You can do that if you would like to. I'm going to choose not to do it that way because the 24 times 4 on the bottom is going to give me a really big denominator. And I know that 24 and 4 have something in common, namely a 4. So instead of doing that, I'd like to keep it smaller, personal preference, and multiply the denominator and the numerator here by 6 to get me my 24 instead. So it is 6 times 35. 210 over 24 minus 142 over 24. What does that give me? 68 over 24. Two options. Well, there's two things you have to do. It's just you have an option of which order to do them in. Problem started out with mixed numbers, so your answer needs to be mixed numbers. So we got to divide this at some point. But it's also true that the numerator and the denominator have something in common. So we're also going to have to simplify. So we can divide first and simplify second, or we can simplify first and divide second. Usually like to simplify first because it makes the division easier, smaller. So in particular, 68 and 24, they're both even at the very least, right? So you could divide them both by 2. So what is 68 divided by 2? 34. And what is 24 divided by 2? 12. Still both even. Divide by 2 again. 34 divided by 2 is 17. 12 divided by 2 is 6. And, whoa, 2. I touched a button. Okay, we're back. Okay, and then to do the division, 17 divided by 6, what will I get? 2 and 5 6. So my answer ends up being 2 and 5 6 what? Yards. Okay, so I think this problem's really difficult for a lot of reasons. One reason is because the fractions denominators are like there's 3 different denominators there, right? You got to deal with combining denominators at least twice. I think it's also harder because the fractions are bigger numerators when I'm working with them than the last one that we did. That makes it more challenging. And then at the end, not only do I have to divide, but I have to reduce and divide. That also makes it challenging at the end. So there's a lot of challenges to this problem that present themselves when we do this with improper fractions. So I'd like to show you what happens then with mixed numbers, not to say that it's necessarily any easier, but so that you can see sort of the complications with that approach and where you might find it to be more difficult. So if we do mixed numbers, we have we're going to pull together, in fact, let me write it again since I don't have it on the screen. 8 3/4 minus 1 7/8 plus 2 3/8 plus 1 2/3. All right, so first things first, that we're going to get all the whole number pieces together. And I didn't do it like this way on other one, but when we're attempting to get them all together, I feel like we might as well go ahead and just distribute that negative through so that I can actually group all the whole number pieces in one place and all the fractional pieces. Are you guys okay with that? So I'm going to actually rewrite this now as 8 and 3/4 minus 1 and 7/8 minus 2 and 3/8 minus 1 and 2/3. So I'm going to put all the whole number pieces at the beginning, and they're all subtractions, so it's 8 minus 1 minus 2 minus 1. And then I've got a positive 3/4 minus 7/8 minus 3/8 and minus 2/3. All right, whole number pieces, 8 minus 1 minus 2 minus 1. Yeah, I've got them all up there. What do we have? 4. We do. There's 2 mixed number pieces that can be combined, so that's kind of, or not mixed number, fractional pieces that can be combined. I have the 3/4, and then I have negative 7/8 and negative 7/3, so that's negative 10/8. I'm not thirds, eighths. Negative 10/8. And negative 2/3. Do you notice anything about the 10 over 8? It can be reduced. You're right, Cameron. It can be reduced. And that's actually kind of nice because they'll divide them each by 2, and what will that give me as a denominator? A 4, and don't I already have a 4 denominator? So that's going to be kind of nice. So let's do that on this problem. So I have the 3/4, and if I divide them by 2, I'm going to get minus 5/4 minus 2/3. So these two can be combined because they now have the same denominator. So what is 3/4 minus 5/4? Negative 2/4. And I've got another 2/3. So tell me about 2/4. It could actually be simplified too if you'd like. You can work with it longer if you wish, but I mean, let me tell you, if you can simplify something, I'd recommend it. So they don't have the same denominator now. I don't have any more simplifying I can do, but this is way better than it began with. So we're going to do our crossing and multiplying. So I have 4, and I have this. Remember that this negative goes with this 1 right here, okay? So I have negative 1, and let's do this negative with the 2, okay? So I have negative 1 times 3, so this is negative 3. I have negative 2 times 2 times negative 2, which would be a negative 4, and it's now over 6. 4, and what is negative 3 minus 4? Negative 7 over 6. So that's kind of top heavy, right? Yeah. So this is really 4 and, ignore the negative for a moment, but this is 1 over 6, right? 1 and 1 over 6. That's what 7/6 is. And if I subtract, do you see 2 more whole number pieces that you can subtract? Absolutely. So this right now I have is 4 minus 1, so that's 3, but the problem is I still have minus 1/6. The 1/6 is still negative. This is kind of a problem, right? Let me show what happens, because I told you what happens if I end up with improper fractions, and I kind of showed you what happened. But what happens now if I still end up with a whole number and it's minus something, not plus? Because if it's plus, I can just ignore this positive sign and smush them together. But if it's negative, it's a subtraction, I can't do that. What do I have to do? Well, I'll show it to you longhand, and then you don't necessarily have to write it out longhand every time. But what we're really going to do is we're really going to take the 3 and we're going to separate it into 2 and 1. That's what 3 is. Agreed? I'm going to leave my 2 the same. And I'm going to rewrite my 1 as 6 over 6. So that I have fractional pieces that I can now subtract. 6/6 minus 1/6 is 5/6. It's literally what you do if you need to go and you need to buy something and you change $1 into 4 quarters, right? You take the $1 and you turn it into 4 quarters. I took away the 1 and I turned it into 6/6. much like my quarters, to get the same answer. All right, so here's what I'm going to do. There's this tiny little bit left, but I don't have time to talk about it and you guys to do group work. I will post the last piece of this as a separate video for you to watch. All right. You will have your 6.1 homework due on Friday. The 6.2 and 6.3 group works, both of those we'll do in class on Wednesday. We don't have class Monday because it's Labor Day. We'll do those in class on Wednesday. So you have homework due this Friday, and then next Friday you're going to have 2 homeworks to be done. So if you wait till Wednesday to start any of that, that's going to be probably a big problem because it's going to be a lot to get accomplished between Wednesday and Friday, okay? But it won't be due until Friday, so I'd encourage you to start the homework for that. Won't be due, but the group work we'll do in class.